Okay, thank you very much for giving me this opportunity to talk here. I would like to present actually this paper here that I wrote together with Lucas Sibera about programmable superpositions of icing configurations. So the topic is the following. So imagine you have a list of data, zeros and ones, and you want to build a magical device that transforms this into a quantum superposition of this data, which means you want a coherent state which looks like this, a pure state. This is sometimes called a QRAM. And the goal of this whole thing is that I basically want to select a polynomial or a small number of configurations from an exponential Hilbert space. So the first proposal, or the original proposal by Seth Lloyd on how to do this, is a digital approach. And as you can imagine, if you want to create such a superposition or select a polynomial number out of an exponential space, this means you need exponential resources. So in this example, you would need an exponential number of beam splitters, and then you have this tree of beam splitters, and so to say the leaves of this tree would be 2 to the n qubits, which actually represent individual configurations. So this means if you do this digitally, you have an exponential number of resources. Now, however, such a QRAM is of extreme importance for many algorithms, and it actually increases the speed if you have something like this of many algorithms exponentially. But then if you look at it a bit more closer, you see that you just shifted the problem from the algorithm into making the QRAM. Now, let's think about Hamiltonian dynamics on the other hand. In Hamiltonian dynamics, we know many systems, atoms, ions, superconducting qubits, where we already have tools to create large many-body superpositions with adiabatic state preparation. Just recent examples would be the 51 qubit in Harvard, but also different superpositions of several hundred atoms which have been created in these systems. However, they are not fully programmable, of course. They are given by the interactions, and what we get is like superpositions of crystals. So is there a way to make them somehow controllable? So in this talk, I would like to present the work where we replace this digital by a Hamiltonian device, which is then based on adiabatic quantum computing. And in particular, the number of qubits is quadratic and not exponential. So we are not trying to beat a classical computer, we try to beat exponentially hard digital quantum computer. I also saw that the AQC logo is now an atom in a chip, so maybe the next quantum computer based on AQC will be based on atoms. So the idea is now the following. Let's start with our Hamiltonian that we've seen now several times. And let's design the classical part of this Hamiltonian, so the final part of the Hamiltonian, and use this as our programming language, so to say, and design it in such a way that the configurations that we want in our superposition in the end are our degenerate ground state of this classical Hamiltonian. So this is where the exponential number comes in, because we want to select a few states from the exponential space, and this can be formally written as a projector. So the projector would basically be here 0 and everywhere else 1. And if we write out the projector in this Ising language, it would have 2 to the n entries. However, we can approximate this, for example, with Hopfield networks or other methods, and get here actually a much smaller number of interactions that we need. And then, if we have this, let's do the following protocol. So let's say we do an anneal, but now we have this degenerate ground state. And if we do this now fully coherently, so no dissipation and things like this, so we have a pure state in the end, and we could hope that we have the superposition that we want. However, as we have seen already today, twice, pioneered by Helmut Katzgraber, we know that this doesn't work, because even in sampling, so if you have incoherent as well, we don't actually get here a superposition. We don't even get all the states. We actually get exponential biases, which means we don't get what we want. And in particular, if you look at it in more detail, we see that this really comes from the problem. So in this spin glass formulation, there is no way that we can actually program a superposition in such a way. So in this talk, I would like to do now two things. First of all, I would like to show you a general theory for the amplitudes if our final state is degenerate. And secondly, I want to show you how we can actually program then based on this theory. So what we do is we first of all identify the problem. So what we have here now is a ground state, and we start here. And then we have a degenerate final state, which means this can never be a fully adiabatic protocol. It actually looks like this. So we have, for large systems now, a region where it's adiabatic. Then there is a point, which is often called the freeze-out point or Kibble-Zurich point, where the amplitudes remain constant. And then we have a diabatic region where the state actually is diabatic between these configurations down here. So because this is a degenerate state, at some point the gap must go to 0, so there will always be a time somewhere along this line where we have diabatic transitions. So this means we can now make a theory where we basically use this freeze-out point as our main point of interest. So we are actually not designing our theory around the final state. We are actually designing it around this Kibble-Zurich point. And the reason is that during the adiabatic evolution, the contributions in our configuration actually change, while in this diabatic region, we have this freeze-out, which means that the contributions don't change anymore. We just have diabatic transitions within this adiabatic manifold. And to do this, there's actually quite an extensive theory to be done, which basically consists of 3 parts. First of all, we define this adiabatic manifold, which means there is configurations down here which we don't leave. So we are adiabatic within this manifold, but diabatic within the manifold. So this we do with some projections. Then we do a Schrieffer-Wolff transformation because it's a degenerate problem. And then on top, we do a perturbation theory with Feynman path diagrams. And doing all this is actually quite a tour de France, which Lucas Sivora did. We get out an effective Hamiltonian, which actually describes the system surprisingly well. And just to show you how it looks in general, imagine we have 3 states, as in this example, which collapse into the ground state. Then the effective theory, the effective Hamiltonian is now really just a 3x3 matrix where the columns and the rows represent these 3 configurations. Now, if you look at the elements on the diagonal, we have something that vanishes quadratically. So this is the same as we would have in a Landau-Sehner problem. Now, if you look at the off-diagonal elements, also vanish, but they vanish with the Hamming distance between the configurations. So this means each of these elements vanishes with a different order in the exponent. And if you ever done Schrieffer-Wolff or perturbation, you know that this is quite painful because it means that you have to basically take into account all contributions from all higher order terms. And then there is also a matrix element in front of this, and this matrix element we can calculate from calculating all Feynman diagrams, which I will show later. So as we've seen by Helmut and Mario today, in the spin glass Ising Hamiltonian, these elements are determined and I cannot change them. So what we then did was, what we always do, we go into our FourBody architecture, and for those who have never seen this before. So this allows one to encode all-to-all spin glass into a lattice gauge model, which has FourBody interactions and a quadratic number of qubits. And the main features are that we can program an all-to-all matrix in local fields, so this makes it local, and all interactions become problem independent. This allows us to implement it in different qubit platforms, and we have now additional so-called gauge degrees of freedom. So what are these degrees of freedom? If you look at the Hamiltonian that comes out, we have single body terms for X and C terms, and then we have these four-body interactions. And what they actually do is the following. They introduce a low energy subspace and a high energy subspace. And the low energy subspace is the original spin glass model. So the energy scales here will be the J's. And they are separated by these constraints. So the constraints are the strengths of each individual four-body interaction. Now, if I change these four-body interactions, this part here remains invariant. And this is also true if I change individual ones. So this means for each plaquette, I can change the constraint strength and still remain exactly in this upper space. The only thing that I change is here the high energy space and actually the whole quantum paths during the adiabatic sweep. Now this we can actually use by saying, well, we have now this effective Hamiltonian where these matrix elements depend on the Feynman paths between configurations, and they definitely depend on the gauge degrees of freedom. So even though the final state is exactly the same, I can actually change all the quantum paths. And this is, so to say, now our strategy. We encode the problem here. This means we still have the degenerate ground state that we want in the end, but we can tune now our amplitudes. And let me just show you how this works. So imagine we want to calculate the matrix element between these two configurations, so 1100 and 1111. Then if I encode this, believe me that it looks like this. We get then 6 qubits and 3 constraints, and the configuration 1100 translates into 2 qubits that point up and 4 qubits that point down, and 1111 translates to all qubits up. So this means the Hamming distance between them is 4. And now how do we get from one to the other? Well, let's just look at all the paths. So here we have our 4 spins down. Here we have all spins up. And we have to go from here to here. So this means in the first step, we have 4 possibilities on which qubit we can switch. For example, we can switch the upper one, we can switch the left one, the lower one, or the right one. If we switch this one first, then we violate this constraint, which gives us an energy C3. If we change this one, we violate 2 constraints, which give us a sum of these 2. If we switch this one, it gives us all 3 of them, and if we switch this one, it gives us the energy contribution of this. Now in the second step, each of the paths has 3 possibilities, so we can, as next one, switch this one, or this one, or this one. And as you can imagine, if we then look at all the actions that we do during these paths, then each of these paths has an individual action which depends on the choice of our constraints. And because we have done this analytically, we can actually turn this around and design from choosing our constraints the amplitudes that we get out in the end. And here I just want to show you an example. So imagine my Hamiltonian with the degenerate ground states looks like this. So I have 3 configurations chosen. In this case, 1100, 11, and so on and so on. And what I want to achieve is, let's say, a fair situation, which means where I have just 1/3 probability for each of these configurations. If I then apply my effective Hamiltonian, I get out as a result 3 numbers for my constraints. And if I compare this now, so the full dynamics with exact Schrödinger equation and an iterative process, you can see here the probabilities of these 3 configurations as a function of the sweep time. And as you can see, they perfectly go to 1/3 in this case. And what's also quite remarkable is how well the theory fits to the full Schrödinger equation. So remember that the effective Hamiltonian had only is only a 3x3 matrix. And now what it makes it programmable is we can also take completely different numbers. Let's say I want 20% this one, 30% this one, 50% this one. I get different numbers, and here as a result I get these final probabilities that I wanted, and we've shown that this is ergodic, at least for the system sizes that we could look at. So this is the group, and I'm actually also looking for a postdoc. So if you're very good, just write me an email. And as an advertisement, next year we will be in Innsbruck. So I would be very happy to see all of you in Innsbruck. Thank you very much.
So do we have questions for Wolfgang?
Hey Wolfgang, thanks. That was a fantastic presentation. I don't know if this is so much of a question as a comment, but I feel like this is a really important subject, an important point for the field, because when we originally built the quantum computers, we had this idea about optimizing or collapsing the system into the classical configuration space. But it's really important to recognize with this work, the work that Helmut Katzgraber and his team have done, and the publication that Mohammed Amin has made about quantum Boltzmann sampling, is that the dynamics of the system are producing a distribution that's during the anneal. And what we need to recognize as a field is that if that is what our engine is, we can use the information we know about Hamiltonians and about quantum systems and about importance sampling to be able to then reshape those distributions to the target distributions we're looking for when we're problem solving and we're trying to produce a computational engine for application. So I thought that was fascinating and excellent work. I'm hoping that we'll see more of this next year.
Thank you very much.
Do we have questions?
How is the scaling of the computational effort when you have to sort of do the combinatorics on all these paths?
This one I know. I thought you were asking about the quantum. So it's actually quite cheap, I have to say. So because in the end, all you need to do is diagonalize. So you have to solve, so to say, a set of equations only for this effective model, which means in the very end, you only have to diagonalize a m by m matrix, where m is the number of configurations that you have in your final state. So actually, that's quite remarkably cheap. Maybe the approximations break down at some point, but for the systems that we looked at, this never happened. So yeah.
Okay, let's thank Wolfgang again.